and the whole project. It's two for ice cube and for something called Can 3. This was for Duman. At any rate, you're trying, what you've got is a bunch of hit times here at phototubes, and this cone of light which is traveling this way at C and this way at C over N. And so you want to take these times and invert these times in some least squared fit to be the coordinates of this trajectory. You can see that that's not going to be trivial. And so it turns out that you can write it by putting in a set of Lagrange multipliers. You can write down an equation where you then set the Lagrange multipliers equal to 0, but you have a set of equations that are a linear set of equations involving the inverse of a matrix. You've got a linear set of algebraic equations which you can invert, which is very cute. You also have to watch out, though, in all of this about dividing by 0. You can get some funny results if you are somehow dividing by 0 in the equations. At any rate, that's just to give you a flavor without giving you all the details of how they can be used. And engineers use them in various systems. And so we'll come back across some examples later in the semester. But I must say, I find the abstract presentation of Lagrange multipliers, I recall when I first saw it, what the hell is this?
Yeah, that's about right.
Yeah.
You can use Lagrange multipliers to derive the Boltzmann distribution.
I don't know how to do that.
Basically, you take like
Another Landau trick?
yeah, also like Boltzmann trick. Like basically, you just take the entropy and you maximize over the entropy, and then you have as a condition average energy as your parameter.
Okay. So at any rate, it's a useful trick. The stuff that you're struggling with, the brachistochrone and these surface minimizations are can be extremely complicated. And they're nice examples of how a system like making soap bubbles solves the problem easily, but it may be a bitch to solve analytically. But it will find the minimal surface energy. And as to the, he goes through all this calculus of variations, but you know, it gets messy with all of the games with extending the derivative, expanding it out, and then once or twice using the trick of partially integrating by parts with the function going between the two extremes in one piece and then flipping the integral over in the other piece, and getting rid of the definite integral at the end points because you already said that it had to be 0 at the end point. So you use that trick, and there you have those equations. But as we said before, you can set it up in slightly different ways. So I think in some sense we've been over all of this material. It is a matter of, in abstract, it's a matter of getting into it specifically. Probably you solved the brachistochrone problem as in undergraduate mechanics anyway. No?
I think I've ever done what I did.
That was horrible. I said I've never.
Not that one in the Earth.
Oh.
The Earth is a horrible case,
Yeah.
relatively horrible case. But the classic one of
Yeah.
what?
Is it the one, you're talking about the one he presented in the book?
The one that's the example, yeah.
This is the classic case.
I've seen it.
I have a particle here, say it starts here, wherever.
Oh, yeah, it's a
And I
particle.
want to draw a wire between here and here and let a bead slide on this wire. And what is the shape of the wire that gets you
They're the fastest.
fastest from point A to point B?
Oh, now I
Come on, you
recognize it.
guys got
Yeah,
it.
cycloid.
Yeah, I've seen that
Cycloid.
before. It didn't really help with the Earth.
No, of course. No, but I'm saying this is the classic brachistochrome problem, and it has a role in the theory of mechanics because it was a problem that people realized. I think it was the first problem where people really sunk in that here I need a functional solution, not just, I'm solving for a function, not just solving a set of equations. And that's what,
Has this ever been applied?
the brachistochrome itself,
Yeah.
I don't know of the applications of it, but practically everything's been applied somewhere. But I don't know where it gets
Slide
applied.
designers.
Yeah.
Slide designers.
You gotta get those kids to the bottom of the slide as fast as you can.
Yeah. Yeah. But I don't think they design them by using cycloids. Do they?
Would be
Both
interesting though.
slides are straight with a little flare at the bottom.
Yeah, it works pretty well, practically.
But you see, the classic problem.
Oh, roller
It's just not
coasters.
obvious. So you might say, okay, let's get going like hell at first and then make the turn and we'll be up to speed for making the transition. Versus saying, well, we'll just go straight down here. Well, it's the shortest path, but doesn't get you going very fast at first. It might be better to have a little drop at first. So the true solution turns out to be, and you guys all know what cycloids are, don't you? Cycloids are wheels rolling, or a point rolling on a wheel. Which wheel can be bigger than this? Rolling on here, and the point might be here. And it's the trajectory that this thing describes as this wheel rolls along. So depending on the ratio of the diameters, it can be this kind of thing, or it can be the kind of thing that goes like this. Right?
Yeah, you can see them in gyroscopes.
Hmm?
Gyroscopes?
Well, yeah, gyroscopes.
No, I used to have a toy like that when I was a kid where we would like put the stencil down and then put your pen in it, go around. in a
But you
circle.
know what, the practical application of these cycloids is actually very ancient. The cycloids themselves, without all of the solution here, but this was how the motion of the planets was described in the Ptolemaic system. And the Ptolemaic system described the motion of the stars on the sky by a set of cycloids like this, so wheels within wheels. And I don't remember how far they got with it, having 2 or 3 layers of wheels within wheels to get the motion right, to describe the apparent motion on the sky of planets which are inside of us, for example. If you look at their motion on the sky, they can't ever get on the outside of us, right? So they make funny motions and then start back again, and this sort of thing. When you plot them in some sort of sky map fixed relative to the Earth. So there's a long history of discussing these kinds of motions, which can all be done in just good old-fashioned geometry, simple plane geometry. So that's a little bit of the history of the problem. So people worried about this brachistochrone, and I think I'm no great expert on the history of the mechanics, but I think this was one of the things that led to the whole idea of the calculus of variations and all this sort of thing.
That's cool. It was Bernoulli who did that.
Hmm?
Bernoulli?
Bernoulli, and I'm not sure who all did, but all these famous names. So, yeah. Right, and the books all tend to show the same old examples, because there's only a relatively small number of fairly simple ones. Everybody does if you look into every textbook, everybody has the hoop rolling on the plane. But life gets a lot more tricky if you let the hoop tip. Right? And the classic, right, let's see. Close the story, keep the noise down, get it done. And, okay, the analogy to electric circuits is good to see. And you will see this many times, that there are these nice analogies between E&M and electric circuit theory, which is not really E&M, right?
Right.
Well,
Special cases.
do you know how an electric potential, how a wave propagates in a wire? Can you get from the E&M that John teaches to Ohm's law, for example?
Yeah, he goes over the
No.
generic form of Ohm's law. Not the specific vehicles
No.
IR, but...
Nobody
related-
derives Ohm's law. Ohm's law is a completely pragmatic thing. We found out that Ohm's law is pretty well true over a large range of magnitudes. Something like 10 orders of magnitude in good materials.
But it's really just an
But
approximation?
it is, yes, an approximation, and it depends on temperature and so on.
Just a damn good
And it is
approximation?
also not derivable from any simple ideas. People are still arguing about resistance in materials and so on. It's a completely observational principle.
So it's basically how I learned chemistry. We don't really know exactly how it works when in high school.
But
They just gave it to us and we do
phenomenology,
it.
right. So the fundamental basis of that part at any rate. Now capacitors and inductors you can write down, get there from the kind of E&M that you're doing, right? Capacitor, just the electric field and two plates, that's straightforward. The inductor being a coil in which there's energy stored in the magnetic field. You can get there, but you still have to hypothesize these electrons moving along in the material with no net charge. So,
I read about Ohm's law last night, and they were saying that he invented it by shocking himself over and over again.
is that right?
Yeah, and seeing how bad the shocks were.
Well, that's an interesting thing because in point of fact, there's a whole lot there's a lot of measurements of various quantities in terms of their
Pain threshold?
physiological response. For instance, your sensitivity to hearing, your ability to resolve pitch, your ability to resolve color, your sensation to pricking pain, your sensation response to electricity. And so it turns out that almost all these things can be plotted. This is really an aside, but almost all these things can log of the stimulus and log of the response. Almost all of these can be plotted as straight lines on such a curve.
On
They're
logs.
power law relationships. And some of these things the physics of physiology. Some of these things we're much more sensitive to than others. And it turns out, relative to your comment, that the one that is steepest is the sensitivity to electrical shock. For no obvious reason, but people go from being they can tolerate, to, oh my God, ah! Whereas there's sensitivity to taste and smell and some of these other things are...
How do you quantify that?
Well, you can quantify that by, pain is a hard one.
Decibels of your scream.
But you can certainly quantify things like your ability to discriminate pitch,
You're right.
color, these kinds of things. Those are good.
That's easy.
But some of these others, it's much more subjective. And, well, we're getting way too far aside. At any rate, I always remember that the steepest one of these is indeed the response to electrical shock. You go from not caring much at all to be driven bananas in a very short range of currents. It's the small currents that get you, not the voltage.
So that's the best torture technique.
Yes.
Most quickly effective.
Any rate, how did we get into that? Yeah, okay. So the analogy to electric circuits, I say, has not too much to do with E&M because Ohm's law is an empirical fact. And like all of these things, requires modification when you get down to the fine details. Is everybody here knows capacitances have leakage currents and have a little bit of inductance to them. If you're designing circuits, you know that they have frequency dependence. And the resistors may have a little inductance and maybe some capacitance. So fine refinements need to be made, and they're all a function of temperature, except the inductance doesn't change much with temperature. But the capacitance and resistance certainly does. At any rate, these analogies are very useful and span across many different disciplines. Heat flow, for example. I was just in my lab here, wrote out the equations for the heat flow. Simple, but we're worried about getting the heat away from the chips. And so we have to cool the whole damn thing. And you can write down something pretty much like this. I didn't write down Lagrange's equations because it's just a simple circuit, but the analogies are there. So you know more physics than you think you know if you think about it, that you can sit down and start solving heat flow problems right away because it's just like resistors and capacitors. Inductors as well, as a matter of fact. So, okay, and one can, in principle, because of that analogy, all of these things you can write down some sort of Lagrangian and solve it. I'm unclear as to when it's really beneficial to use the formalism, however. I think basically when the system gets to be pretty complicated. Okay, so we said we would come back today and finish up some of the problems from the first chapter. Okay. Here were your problems from homework number 4. Where did we leave off anyway?
I think it was, the last time we did problems was me, John, and Jake.
I think we did the first 2 homeworks for sure.
Okay.
We did the first 2, and that was me and John, and then Jake did the first one, or one of them from the third homework.
Okay. Does somebody want to do we didn't do the rocket problem, right? Oh, yeah, we did the point transform. I guess we left off at 13.
That's right, mine wasn't in there. I had to email it to you. Do you still want it? Like the physical copy?
No, not necessarily. I passed it on to Kata. Actually, that one is not very hard, didn't it? Do you want to spend time on the rocket problem? The main thing is to realize that n is a function of t when you write it down. That's the first example where we have. Somebody want to do that, or is it worth even talking about?
I think I'm good.
Everybody happy with the,
Yeah, I'm okay with the rocket.
okay. That was number 13.
It's not on this somewhere.
It's a previous assignment.
Previous assignment, yeah.
I mean, I only got like, I think I got 271, which wasn't very, as close to 300 as I
Well,
wanted.
okay,
But,
I don't care about the numbers. As long as you didn't get 2 to the 17th or something.
Yeah,
10
5.
2 times 10 to the 17th or something like that. Okay, 16 was the classic one of particle moving in a plane with a central force. Did you guys do 16?
Got 17, 18, 20, and 23.
Yeah, I
We
can
did.
see. I had marked it in here, but then I think I crossed it out.
oh, I think I'm missing one of my homework sets.
We did, but I think we got it back last time.
Oh, no, I know what it is.
Oh, okay, yeah, I had thought about giving you number 16, and then I didn't, because actually we're gonna do that again later, central forces. 17, what about 17?
We did do that.
Yeah, 17 is
Yeah.
straightforward.
So someone wanna talk about 17?
I can do it.
Okay? Not at all. This is in fact a nice example of one of those nasty mixed systems where one piece is classical and one piece is relativistic, which fortunately won't bother us much at this point, but does make the point of why it's good to stick with momenta. Stick with the momenta and you will be saved.
So you got your classic nucleus, it's shooting out an electron and a neutrino at right angles, so that makes it relatively easy. So basically you do conservation of momentum. So in the X, I've got the neutrino, which was 1
Wait, he's in 17?
MeV
Oh,
C. And in the Y direction, you've got the electron. It was 1.73 MeV C, and I was worried that it was relativistic, so it would mess it up, but it's still just as simple as basic mechanics.
Because you stuck with the momentum.
Right, exactly. So you pretty much just do the momentum of the nucleus is x squared. Three. 2. Oh, nice number. And then you need the angle. So you can pick whichever angle you want. I guess I did the x. So what did I say here? Px. N cosine theta. Where dot, 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 dot. We know it's going to go this way. So I did it like this. Oh no, it's not. Sorry. So pretty straightforward.
Wonder why that's on.
So it's 60 degrees. And I did the, I guess, kinetic energy is pretty easy because it's just K equals P squared over 2M. I was thinking it's relativistic, so I used K equals PC, which would give you 2.0 MeV. But according to this, it's not relativistic.
Why isn't it relativistic?
I guess the energy's not high enough to, I thought it was high enough, but
For the neutron, it's